Hi, my name is Daniel from CSC 1202 Computer Organization Group 6, and in this video, my group and I are going to be talking about computer memory. First off, what is computer memory? Computer memory is a hardware device or system that is used to store data to be accessed immediately by related computer hardware as well as electronic devices. For now, there exists only two types of memory. Those are primary memory as well as secondary memory. Primary memory is a storage solution that holds temporary data that is accessed directly by the CPU. It usually holds data such as the results from arithmetic operations as well as the instructions of the arithmetic operation itself. On the other hand, secondary memory is a storage solution that offers long-term, permanent storage of data. One important thing to note is that the storage unit for memory is called a byte, which is the equivalent of 8 bits. Also, memory can be categorized as volatile and non-volatile, as well as erasable and non-erasable. Volatile memory is when the information in the memory decays over time and needs constant refreshing to maintain the information. When power cuts off, the memory will lose its data content. Non-volatile memory does not need refreshing to maintain data and therefore does not need power in order to maintain the data. Erasable memory is when the data in the memory can be rewritten. Non-erasable memory is when the data in the memory is prefabricated and unchangeable. Now that we know the basics surrounding what computer memory is, let's take a closer look at one of its types called primary memory and how exactly primary memory works. Primary memory, also known as main memory, is made from a collection of semiconductor memory cells. Each individual memory cell can exhibit only two different states of output. These two different states are what determines a binary 1 or a binary 0 to the computer. The semiconductor memory cells each have three different terminals that can carry electrical signals. Each terminal carries out a different purpose or function for the cell. Firstly, the cells have what is called a select terminal. The select terminal essentially selects the specified memory cell where a read or write operation is to take place. Secondly, the cells also have a control terminal. The control terminal indicates the operation to take place on the selected cell, which can either be a read or write operation. Lastly, the third terminal effects or carries out the actual operation indicated by the control terminal. For example, in the scenario where a read operation is indicated by the control, the terminal communicates or rather reads the current state of the selected memory cell. Conversely, in the scenario of a write operation being indicated, the terminal updates or writes the new state of the selected cell. RAM is a form of primary memory that can be read or changed in any order, and is typically used to store data from calculations as well as machine code. The two main types of the volatile RAM are static RAM, otherwise known as SRAM, and dynamic RAM, otherwise known as DRAM. DRAM is made with cells that store data in the form of charge and capacitors. The presence or absence of charge in a capacitor is interpreted as a binary 1 or 0. Because capacitors have a natural tendency to discharge, DRAMs require periodic charge refreshing to maintain data storage. The word dynamic refers to this tendency of the stored charge to leak away, even with the power being continuously applied. DRAM is also asynchronous, which means it does not sync to any external influences. Because of this, the basic form of DRAM is not going to be as fast as the more modern and complicated DRAMs offered today. Unlike the traditional DRAM, which is asynchronous, synchronous DRAM, also known as SDRAM, exchanges data with the processor synchronized to an external clock signal. This makes it faster than DRAM. Double data rate DRAM, also known as DDR DRAM, is the more common form of RAM typically found in today's desktops and servers. It uses a clock rate and fetch data rate that is double that of today's SDRAM. Now, let's take a look at static RAM, otherwise known as SRAM. SRAM is a type of RAM that retains data bits in its memory as long as power is being supplied to it. It is able to do this by using latching circuitry, more commonly known as flip-flops, to store each bit. When comparing DRAM and SRAM, we find that the only similarity between them is that they both must be continuously powered to preserve their bit values. On the other hand, here are some of the many differences between them. The cell found in DRAM is simpler and smaller than an SRAM. DRAM has a larger storage capacity than SRAM. DRAM is also typically slower than SRAM. Because DRAM is slower and has larger storage capacity, it is used for the main memory. SRAM, however, is used for cache memory. ROM, or read-only memory, is a non-volatile memory. As its name suggests, the data in ROMs can only be read. ROM allows data or programs to be permanently stored in the computer's main memory. So, data will be readily available to the computer without having to access external storage. The contents of the memory are predetermined, and data is programmed during the manufacturing process. Therefore, ROM fabrication is quite intricate and errors must not occur, or else a whole bunch of ROMs may not be functionable. There are a few variations when it comes to ROMs. We have the PROM, programmable ROM, and the read-mostly memory. PROMs are non-volatile. They may only be written once after being manufactured. Read-mostly memory, however, can be written repeatedly. It's non-volatile as well, just that the read operation will be far more frequent than the write operation. When it comes to PROMs, we do have some upgrades, which are the EPROM, Erasable Programmable Read-Only Memory, and the EEPROM, the Electrically Erasable Programmable Read-Only Memory. Wow, what a mouthful. Contents of EPROM can be repeatedly erased by shining intense UV light onto the memory cells. This feature makes it more expensive than PROM. The EEPROM is in a sense a superior version of EPROM. It allows write operations to be performed anytime, making it very flexible in terms of application. It is more costly than EPROM, but it does have a lower storage. Next, let's talk about flash memory. Flash memory is an electric, non-volatile memory storage. It is an intermediate between EPROM and EEPROM in terms of cost as well as functionality. Blocks of the memory, or even the entire memory itself, can be completely erased in a single action, thus how we get the name flash. When it comes to flash memory, there are two types, the NOR flash and the NAND flash. Their main differences are that on the NOR flash, the memory cells are connected in parallel to the bit lines, whereas on the NAND flash, the cells are connected in series with the bit lines. This difference in architecture brings about their distinct properties. Firstly, NOR flash allows random access, whereas NAND allows page access. Besides that, NAND flash is smaller in size than NOR flash, which makes it cheaper and enables more bits to be assembled into the package, offering a higher storage capacity than NOR flash. Although NAND flash might seem to be the better option, both NAND flash and NOR flash have their own application. We finally did it. We are now able to talk about the last type of primary memory, which is called cache memory. The cache memory is one of the most crucial forms of primary memory found in the entire computer architecture. Caches are registers internal to the processor which are constructed from SRAM cells. As we know from before with SRAM cells, it is a volatile memory, which means that data is erased when power supply to it is cut off. The cache memory, although being super essential, is actually the smallest memory structure found in the entire computer, consisting of multiple tiny layers. The L1 cache is the smallest in the cache memory architecture and is located closest to the processor core, allowing for the fastest route of access. Nowadays, modern computers have cache layers up to the L3, and some high-end servers and mainframes even have an additional L4 cache. Based on the architecture diagram displayed on the left, we can see that the L1 and L2 cache are private to each processor core with a total of 8 cores in the processor chip. Resources from the L3 cache are shared among the 8 cores within a single chip, and each processor chip shares its resources via the additional L4 cache if present. Data transfer from larger main memory, such as from the RAM to the CPU, is somewhat slow when compared to the fast processing speeds the CPU is actually capable of. Therefore, caches are used to facilitate the data transfer between the main memory and processor. This must be done at speeds which match the rate of computation the processor is able to carry out. The reason cache memory can support such high data transfer rates is due to the data being stored in the cache memory itself. When data is stored in the cache memory, the data is readily available for use by both the CPU or even the main memory. Due to this, data transfers may feel somewhat faster if the data is frequently accessed by the user. Although the primary memory is essential for CPU operations and computer design, the primary memory cannot permanently store programs or large sets of data. Since it is volatile, it is only capable of storing basic instructions required to operate the computer, as well as data from arithmetic calculations. That is where the secondary memory comes in, presenting a solution to long-term permanent storage of software and data. Many different types of secondary memory exist, and even today, one of the most widely used forms of secondary memory is the magnetic disk. This type of memory can be found in virtually all computers in the world, as it has been the standard for secondary memory ever since it was created. One of the most common types of magnetic disks can be found in the form of hard drive disks, otherwise known as HDDs. A magnetic disk primarily consists of a rotating magnetic surface called the platter and a mechanical arm that moves over it. Together, they form what is known as a comb. There is also a conduction coil called the head at the edge of the mechanical arm. Well, most systems have two heads actually, the read and write heads, and they are used for, you guessed it, reading and writing data. And its basic function is through a rotating platter that spins underneath the heads, which are stationary. Well, you might be wondering, how does it even operate? The data on a magnetic disk is written and read through a process called magnetization. The platter spins and maintains it at high speeds while the head of the arm moves across its surface. Since the whole device is sealed airtight, the head floats on a thin film of air. So, when a small current is sent to the head, magnetic patterns will be made and diff patterns are produced for positive and negative currents. This causes the creation of tiny spots to be made on the disk surface so it becomes magnetized and data can then be stored. Vice versa, a small current could be applied to those tiny spots to produce the same polarity as previously recorded on the platter when the head needs to be read. Magnetic disks do have their ups and downs. The good thing about them is that they aren't expensive because they are relatively easy to find. They can also store a larger volume of data compared to its alternative solutions. Plus, glass substrates have been recently used to replace the weaker aluminium substrates used traditionally, which makes the disks less prone for errors in reading and writing, more reliable, and more durable towards shock and damage than previous iterations. But they are still able to be damaged when dropped, have slower read and write speeds, which overall make them less compelling than other secondary memory options. Another popular secondary storage device is called the SSD, or a solid-state device. Two key components of it are the flash controller and NAND flash memory chips. It is used in consumer products such as personal computers, computer games, digital music players, smartphones, tablets, thumb drives, and also even incorporated with graphics cards. It uses integrated circuits, or ICs, to store data. The term solid-state refers to electronic circuitry built within the semiconductors. Do note that it is sometimes called a solid-state drive or semiconductor storage device, but also it is incorrectly called a solid-state disk due to the lack of spinning disks. The SSD reads and writes data to an underlying set of interconnected flash memory chips, which uses floating gate transistors, or FGTs, to hold electrical charge, which thus enables the SSD to store data even when it's not connected to a power source. Each FGT contains a single bit of data, designated 1 for a charged cell or 0 if the cell has no electrical charge. The SSD uses three main types of memory. Single-level cells, which are SLCs, can hold 1 bit of data at a time, a 1 or a 0. This is the most expensive form of SSD, but rightfully so, as it is the fastest and is also durable. Multi-level cells, or MLCs, can hold 2 bits of data per cell and have a larger amount of storage space in the same physical space as SLCs, but it does have a slower writing speed. Triple-level cells obviously can hold 3 bits of data in a cell. They are on the cheaper end but have slower write speeds and are less durable than others. Some of the advantages of SSDs over HDDs, the hard disks mentioned before, are the high performance offered when they are able to compute more input-output operations per second. They also lack the rotating mechanism, which means that they have a longer lifespan because it does not have mechanical wear. They also exhibit high mobility because they are lighter in weight, and they are quieter and cooler. Lastly, they also consume less power. Here we can see some of the comparisons between NAND flash drives and a Seagate laptop internal HDD. NAND flash drives have a higher write speed of 200 to 550 megabits per second. Flash drives also use less power, thus having a longer battery life. Although flash drives have a smaller storage capacity and typically cost more, the cost of flash-based SSDs have actually dropped while having an increased performance and bit density. Now it's time to move on and talk about optical memory, which is any storage type that has data written and read with a laser. The first type we'll look at is the compact disc, otherwise known as the CD. All types of CDs are constructed from polycarbonate, which is essentially just strong, transparent thermoplastic resins used in molding materials. The data is imprinted on a series of microscopic pits on the surface of the polycarbonate. The surface is then coated with a highly reflective acrylic layer to protect it from dust and scratches. CDs are read using low-power lasers that shine through the disc, which is being spun on a motor. The varied positions of the light due to the unevenness of the disc is reflected back to a photosensor and is converted into a digital signal. This photosensor captures the laser at regular intervals and calculates binary values based off the variation in elevation of the light reflected. The main difference between the three types of CDs, which are the CDR or the CD readable, the CDRW, the CD rewritable, and the CD-ROM, the CD read-only memory, is that the CDRW can have its data rewritten many times, whilst the CDR can only have data written on it once, and the CD-ROM comes with predefined data which cannot be overwritten. Let's also quickly compare two different types of optical discs called the Digital Versatile Disc or DVD and the High Definition DVD or HD DVD to the previously mentioned CDs. The main differences are DVDs have 7 times the amount of data capacity compared to CD-ROMs, bits are packed more closely on DVDs, and DVDs can employ a second layer of pits on the other side of its surface. Last but not least, we have magnetic tape. Magnetic tape is composed of a flexible plastic or polyester that is coated with a magnetizable material. They often come packaged as open reels or are housed in cartridges. On the modern hierarchy of memory today, magnetic tape has the slowest rate of access, and in combination with it being relatively cheap to manufacture, it therefore has the lowest cost. Because of this low cost and slow access speed, magnetic tape is often used for data archiving purposes. It must be mentioned, however, that magnetic tape is prone to suffering from degradation and therefore is not an ideal solution to long-term archiving. How exactly does it work, you might ask? Data is read or written via the contiguous memory blocks, also known as the physical records, on the magnetized coating on the tape. When data is being written, the first set of bits is recorded along the whole length of the tape. Once the end of the tape has reached, the heads are repositioned and the bits are again recorded along the whole length of the tape, but this time in the opposite direction. This process repeats until the tape is full and its maximum capacity has been used.